Hi everyone, I'm Hossein Shokri Kadikolai from KTH Royal Institute of Technology in Sweden, and I'm going to present our paper on communication efficient variance-reduced stochastic gradient descent. This is a joint work with Sindri Magnuson. This paper is about distributed optimization and developing efficient algorithms to realize that. But one may ask why we need distributed optimization in the first place. So there are many different reasons. For example, consider a scenario where we want to learn a common model with local datasets. Those datasets could belong to different hospitals, and there is a master node or a server who wants to find some common pattern like a drug from the data is locally available to those hospitals, but they don't want to share the actual data. So in that case, we are talking about some form of distributed optimization while we are preserving privacy of the local datasets. The second scenario could be distribute the computational loads. So imagine that at the master node, we can have all the data, but we are talking about billions and billions of high quality images, and we may not even be able to store all those data. So, or even if we can store the data, we cannot do all the computations locally. So in that case, we do prefer to distribute the workload of the computations among different workers. And that actually goes very well with the recent concept of edge computing. In general, running a distributed optimization, especially in large scale, it would be very challenging due to usually large dimension and the communication overhead, as we will see. In the rest of the presentations, I will first introduce some general concepts and then we'll go to our quantized modified SVRG algorithm. I will then show some experiments and conclude this presentation afterward. A stochastic gradient descent is a common approach to handle big data, but it suffers from the variance. So what happens is that if you use a stochastic gradient descent with a constant step size to have a good convergence, you're gonna converge very fast to an uncertainty ball, and then you're gonna just oscillate in that ball simply because there is a noise in the gradient and you cannot do anything more than that. But there have been a lot of recent works on different approaches to reduce the variance of that gradient as the iterations evolve. One of these algorithms is SVRG, introduced in 2013. It follows the general skeleton of stochastic gradient descent, but with some minor differences. There are two loops, outer loop and inner loop. In the outer loop, the master node will compute all the gradients and store the average gradient. So now we have a true gradient computations at the outer loop. The master node then uses these noiseless gradients to reduce the variance of the gradient estimations in the inner loop. So there are gonna be T inner loops, capital T, and inside the inner loop, instead of updating only based on the new gradients or the current gradient, I'm gonna add this blue new term to that so as to reduce the variance. And it has been shown that these iterations will actually converge very fast, much better than stochastic gradient descent in many class of problems. While SVRG improves the convergence rates of stochastic gradient descent in terms of the number of iterations, still it suffers from a high communication cost. At every iteration of the inner loop or outer loop, we do need to send a lot of gradients from the workers to the master node and also the parameters back in the downlink channel from the master node to the workers. To address the communication cost, there have been a lot of works on one-way and two-way quantizations, where the algorithms updates based on the quantized version of the gradient. So essentially the nodes, they don't send the full gradient, but a compressed version of the gradients. And also the server can send, instead of the actual parameter, a quantized version of the parameters. But many of those class of algorithms, they may not actually converge to the optimal point, or we may need to increase the number of bits as we move on, because essentially as we move on, the magnitude of the gradients will go down and down. This is the first order optimality, that the gradient should vanish at the optimality. And it's going to be very challenging to quantize with a fixed amount of bits, like 2 bits or 3 bits, and still preserve the convergence to the optimal point. Besides that, there is another class of algorithms that avoid some communication rounds, and they are essentially based on two different set of algorithms. The one that defines some predefined schedule, like upload every kth iterations, or they are based on some self-triggered exchange where you every node they're gonna locally compute some parameters and then decide if they should upload their gradients or not. This paper actually focuses on compressed communication information. Our main research challenges are how to incorporate local optimization landscape to design an efficient quantizer, and is it possible to analyze the robustness of these quantized algorithms to the number of bits and then see how it behaves if we change the number of bits used for the quantization? One of the main parts of our paper is adaptive quantization grid, where instead of representing W in a real number, we're going to project that to a lattice like this one through some projections called Q, which is like our quantizers. We call it adaptive because this quantization space will change actually based on the landscape of the optimization and for individual coordinates actually. So at the very beginning, we don't know really where W is, so we have to make a very big space to be able to cover all potential W to ensure that W will remain inside this quantization space. But as we move on, can reduce the size of this space, and the same number of points, now we can have a higher resolution to show one specific point in that smaller space now. So this is the whole idea, to essentially shrink down this quantization space as we move on based on the optimization landscape. So in general, this quantization grid is defined based on a center C, a radius RWI with respect to coordinate I, and a quantization operator Q. And as we said already, the quantizer would map W, which is like the parameters or the gradients or whatever that you want to quantize, to one of the coordinates using this mapping. The actual quantizer that we're going to use is unbiased random quantizer, which projects this W to Q of W, one of those four lattice points close to W, to ensure that the expectation of Q of W is identical to W. This is the pseudocode of a general quantized SVRJ algorithm. So it's essentially very similar to the actual SVRJ algorithms with three main differences. The first one is that in the outer loop at every iteration, we do need to define now the quantization space for both parameters and also the gradients RWK and R zeta and K. Then in the inner loops, instead of updating based on the actual gradients, we're going to update based on the quantized version of those gradients in step 8 and 9. And also in step 10, instead of updating now again based on the actual U, which is like the parameter, we're going to update based on the quantized version of that. And by updating, it means that the server gonna send the quantized version of this parameter, and then the nodes in the next inner loop, they compute the gradient with respect to that quantized version that the server sent. One of the challenges that we had was that with the original SVRG, we couldn't ensure shrinkage of the quantization space. So we couldn't really design some adaptive quantizer efficiently. So we had to modify this SVRG by adding a memory unit. So what happens is that we're going to save the parameters and gradients of the last step at the server, and at the next iterations at the end of the inner loop, we're going to reject new solution W tilde K if this new solution leads to higher gradient norm at the server. And in that case, the server will go back to the previous solution actually, and then continue the iterations from that. We can show that using this very small modification, we can now have 1A and 1B, which essentially says that the new W tilde K plus 1 inside a circle centered at the previous parameter and with the radius of RWK. So that could be actually our quantization space for W to ensure No matter what wk plus 1 is, it's gonna reside in that circle or in that quantization space. The same actually goes for the gradients. So then we can say that the next gradient, no matter its value, it's gonna be inside a circle centered at the previous gradient, the radius of rgk. This proposition shows the convergence of quantized SVRG algorithm with a fixed quantization space for a class of strongly convex and smooth functions. So if we consider a URQ as our quantizer, and as I said already, fixed quantization grid, under some conditions, technical conditions, we can ensure that the convergence would follow delta k plus 1, and delta k is like the difference between expected f of w tilde k minus f star, so how close we are to the optimal point. Delta k plus 1 minus some gamma k gonna be smaller than sigma k times delta k minus gamma k. So what does it mean? It means that we have a similar rate of convergence as original SVRG, so a linear rate of convergence determined by the sigma parameter, but instead of converging to the optimal point, we will converge to an uncertainty area whose radius is this gamma k. And this gamma k is actually, if you look at the paper, it's a function of the combined quantization errors of the gradients and parameters in the inner loops. Now, if we change the fixed quantization space with the adaptive quantization space for the same class of functions, we can recover the same asymptotic convergence rate of the original SVRG, but now with a fixed number of bits. We don't really increase the number of bits per iteration. The only thing that we change is that we shrink the quantization space actually to make sure that with a fixed number of bits, now we can have a more resolution for parameters and for the gradients. And if you look at the equations, then you're going to see that the bit scaling is in the order of d some log factors, which is totally negligible. But then again, the complexity here is linear in D, which can be further reduced if we use some coding techniques. So now let's look at some experiments. We have considered the MNIST dataset and logistic reach function for classification, and also one versus all technique. We have also many different benchmarks. The unquantized benchmarks that we have are SVRG, modified SVRG, gradient descent, stochastic gradient descent, and SAG algorithm. And then we do have a lot of quantized version of those benchmarks as well, including a quantized version of MSVRG using a fixed lattice. We call it QMSVRGF. So quantized modified SVRG with a fixed lattice and with adaptive lattice, also QGD, QSGD, and QSAG. And then we also have a plus version of those QMSVRG, and the only difference is that in the plus version, we do quantize actually all the gradients in the inner loop. So if you go back and then look the actual algorithms, for some technical reasons actually that we needed for the proof, we had to quantize only one of the gradients in the inner loop and send the unquantized version of the others. But that was only for some technical reasons. But in the simulations, we don't actually do that. And then we will see that nothing gonna happen in terms of convergence actually. This figure shows the classification performance for b divided by d equal to 7, so the number of bits per dimension 7. The top figure shows the loss of the training as a function of the iteration k, and the bottom figure shows the gradient norm, so essentially the first order optimality conditions, again against iterations k. And then we do have many different benchmarks here. So the takeaway here is that if we do some form of heavy quantizations, some of the existing algorithms like gradient descent, so the quantized version of that gradient descent, of course, or SGD, or even SAG, they may not actually converge. So we do need to incorporate some other complementary algorithms like error feedback framework. Whereas in our algorithm, by only carefully designing the quantization space, we can recover the optimal solution with a much fewer number of bits per dimension. And of course, if you add on top of that error feedback framework and other class of algorithms that ensures convergence with a fewer bits, then we can save even more. More importantly, if you look at the QMSVRGF and QMSVRGA, then you're gonna see that they actually follow pretty good MSVRG modified version of SVRG and also the actual SVRG. So we don't really lose almost anything in terms of the convergence, but we save a lot in terms of the number of bits. To conclude these presentations, we have developed a new framework for two-way quantization of SVRG algorithm. It's based on an adaptive quantization grid to maintain the convergence rate of SVRG with a finite and small b actually. The whole idea is to make sure that the grid follows the geometry of the optimization landscape. We have a lot of reduction in the communication overheads by as much as 95% actually, with almost no effect on the convergence rate. It also can be very well complemented by error feedback framework and other approaches to further improve the convergence with a fewer bits. And finally, we are now looking at combining it with some self-triggered intermittent uploads where we don't really send these gradients, even the quantized version of the gradients at every step, but whenever those gradients are actually needed and have some major contribution to solving this optimization problem. Feel free to contact me should you have any questions or curiosity. Thank you.